Welcome to this RIBA certified CPD presentation on concrete repair and protection to BSEN 1504. Before we start, here's some information about Ronacrete. Ronacrete is an international manufacturer of construction products. We specialise in several applications, such as resin-bound and bonded surfacing, waterproofing, screeds, flooring, bedding, and of course, concrete repair and coatings. Established in 1969, Ronacrete has two main production centres, Essex, our European HQ, and Hong Kong and China, which serve the Far East. The company was started by Maurice Osin and is still a privately owned family-run business. Ronacrete has provided products for some of the most iconic structures in the world, including the Shard in London, the Hong Kong Shanghai Bank, the Houses of Parliament, Wembley Stadium, Disneyland in Hong Kong, and many more. Since Ronacrete's incorporation in 1969, we have been awarded many accreditations and certifications. BSEN ISO 9001, BSEN ISO 14001, and OHSAS 18001 ensure all our products are manufactured to a high quality in environmentally friendly and safe conditions. 6 BBA certificates have been awarded for a range of applications, and all necessary products have been CE marked with declaration of performance documents available. Ronacrete products can be found on a number of specification sites, including RIBA Product Selector, NBS Plus, and NBS BIM. Ronacrete is also a member of many trade associations including Bali, the Concrete Society, FERFA, BSWA, BEMA, and the Concrete Repair Association. All required products are tested for slip resistance in accordance with BSEN 8204, Part 6, 2008. The aim of this CPD presentation is to gain a knowledge and understanding of the following in relation to concrete repair: standards, diagnostics, causes, product ranges, and long-term protection. Standards covers BSEN 1504 and the standards that should be adhered to when specifying concrete repair systems. Diagnostics covers the various techniques used for condition surveys and corrosion diagnosis. Causes covers the causes of concrete damage and corrosion, as well as appropriate repair methods. Product range covers the range of repair materials and their application. Long-term protection covers the various methods and materials available to provide long-term protection to concrete. Introduced in September 2006, BSEN 1504 is Britain's first standard for concrete repair. It covers the whole concrete repair process, from initial identification of a problem through to works being carried out on site. From a specifier's point of view in particular, it requires a whole life cost approach, so the anticipated future needs of the client are met. Health and safety considerations should conform to the Construction Design and Management Regulations 2015, which state that all parties involved in a project have a responsibility to health and safety, from client to architect to main contractor to subcontractor. The following should be assessed when health and safety is being considered: the safety of occupants, the safety of pedestrians, the safety of site staff, for example, whether adequate protection has been provided, the provision of health and safety information for products used. Environmental considerations are also key throughout the planning process. The following should be considered at this point. How will your chosen repair methods impact the surrounding area? Could the work cause contamination of surrounding environment? Will the environment dictate what the repair method will be? For example, can shot blasting be carried out in a busy town centre with pedestrians passing by? Or will alternative methods of preparation need to be implemented, resulting in a longer, more expensive process? The client's objectives are very important. As part of providing the best advice, you should disclose whether a full concrete repair and protection scheme is truly required. For example, a client may only have short-term plans for a building and the remedial work and associated costs should reflect this. The following should be taken into consideration when looking at the client's objectives: finance, future requirements of the building, determination of the overall life expectancy of the structure. It's important to fully understand the causes of concrete damage and corrosion, assessing why deterioration has occurred and looking at how it can be avoided in the future will enable you to specify the most appropriate repair methods and materials. When specifying concrete repair works, the following should be considered. How will noise and dust brought about by the works affect the surrounding environment? Will the structure be weakened while work is being carried out, and will it require additional temporary support? How effective will your chosen repair method be on preventing or slowing down deterioration? What will the appearance of the repaired concrete be? Will it be aesthetically acceptable, or will further finishing products be required? How durable will the repairs be? Will they meet the client's requirements? Once all of this has been considered, you can start to put a plan of action in place. As well as specifying the standard items of work such as access, cleaning, preparation, repair methods and materials, it's important to include progressive investigation and testing as works proceed. Concrete repair inevitably involves carrying out destructive work before reinstatement. This may expose previously unknown problems which require a different approach. For example, removing a larger than expected portion of concrete column may result in additional strengthening requirements, and also a different technique to that specified for the repair. It's usually difficult to produce a very accurate bill of quantities when it comes to the amount of concrete repair required. The full extent of preparation and, in particular, the true amount of repair material can't really be gauged until work has commenced. Therefore, it's beneficial to allow for a remeasure during the repair process. Concrete repair projects vary enormously in scale and cost, particularly when access issues arise. Most concrete repair contractors have their own specialities and are better suited to one type of project than another. When compiling a tender list, it's important to ensure your selected contractors are suited to the proposed work. Manufacturers can assist with recommending the most appropriate contractors. Work inspections are necessary to ensure consistency of quality and adherence to the required standards, awareness of the changing state of the building as works progress. A lot of time and effort will have been put into carrying out investigations, specifying repair methods, and preparing contract documents, so it's essential this is implemented on site. As well as ensuring best practice is carried out, site inspection allows you to continually assess the changing state of the building. We'll now look at different types of concrete damage and how they occur. Concrete can deteriorate for a variety of reasons, and concrete damage is often the result of a mechanical, physical, or chemical attack. The most damaging forms of deterioration in above-ground concrete structures are carbonation attack and chloride attack, which cause corrosion of reinforcement and consequent spalling of concrete cover. Sulfate attack is a common cause of damage to below-ground structures, which reduces the strength and cohesion of the concrete. The effects of CO2 attack can be reduced by using concrete with a low water-to-cement ratio and a high cement content. Capillary pores in such concrete are smaller and less connected. A common form of impact damage occurs at slab edges of joints on vehicular traffic surfaces, particularly where settlement of concrete bays has occurred, exposing the sharp arris to damage. Impact by vehicles on highway structures and loading bays is also common. Properly designed and constructed concrete members are usually strong enough to support the loads for which they are intended. Overloading can occur when a change in use of a structure takes place without structural upgrades. Extreme weather and geological events can cause overloading of structures, although this is uncommon in the UK. Overload damage can occur during construction when concrete hasn't reached design strength. Early removal of formwork, or the storage or operation of heavy materials and equipment on and around the structure, can result in the overloading of concrete elements. Thermal movement is a common cause of cracking in buildings, as materials expand and contract during thermal cycling. Introduction of appropriate joints in reinforced concrete structures will reduce the potential of cracking. Concrete subjected to sustained loading exhibits gradual deformation, known as creep. There are also times where damage to concrete might prove to be too extreme to consider repairs. In extreme conditions, wind vibration can cause catastrophic failure of structural elements such as bridge decks. But other than minor cracking, damage to concrete caused by machinery in factories and by vehicle traffic on bridges and multi-storey car parks is unusual. In most concrete, aggregates are more or less chemically inert. Some aggregates react with the alkali hydroxides in concrete, causing expansion and cracking over a period of years. Alkali aggregate reactivity has two forms: alkali silica reaction, or ASR, and alkali carbonate reaction, or ACR. ASR is more problematic than ACR, since aggregates containing reactive silica materials are more common. Aggregates containing certain forms of silica will react with the alkali hydroxide in concrete to form a gel that swells as it draws water from the surrounding cement paste, or the environment. In absorbing water, these gels can swell and induce enough expansive pressure to damage concrete. Typical indicators of alkali silica reactivity are MAP cracking, and in advanced cases, closed joints and spalled concrete surfaces. The chlorides and nitrates of ammonium, magnesium, aluminium and iron all cause concrete deterioration, with those of ammonium producing the most damage. Most ammonium salts are destructive because, in the alkaline environment of concrete, they release ammonia gas and hydrogen ions. These are replaced by dissolving calcium hydroxide from the concrete. The result is a leaching action, much like acid attack. Alkalis of over 20% can also cause concrete disintegration. As the water in moist concrete freezes, it produces pressure in the capillaries and pores of the concrete. If the pressure exceeds the tensile strength of the concrete, the cavity will dilate and rupture. The cumulative effect of successive freeze-thaw cycles and disruption of paste and aggregate can eventually cause significant expansion and cracking, scaling and crumbling of the concrete. Concrete with low permeability is better able to resist the penetration of water, and as a result, performs better when exposed to freeze-thaw cycles. The permeability of concrete is low when the water-to-cement ratio is reduced, and water-reducing agents can improve workability. Concrete changes slightly in volume for various reasons, the most common causes being fluctuations in moisture content and temperature. Contraction can cause cracking if the tensile stresses that develop exceed the tensile strength of the concrete. When water evaporates from the surface of freshly placed concrete faster than it's replaced by bleed water, the surface concrete shrinks and tensile stresses develop in the weak, stiffening plastic concrete, resulting in shallow cracks of varying depth. Plastic shrinkage cracks can be prevented by taking measures to prevent rapid water loss from the concrete surface, such as plastic sheeting or curing agents. Almost all concrete is mixed with more water than is needed to hydrate the cement, and much of the remaining water evaporates, causing the concrete to shrink. Restraint to shrinkage, provided by the subgrade, reinforcement, or another part of the structure, causes tensile stresses to develop in the hardened concrete. Restraint to drying shrinkage is the most common cause of concrete cracking. Control joints are placed in concrete to predetermine the location of drying shrinkage cracks. Drying shrinkage can be limited by keeping the water content of concrete as low as possible and maximizing the coarse aggregate content. Abrasion damage occurs when the surface of concrete is unable to resist wear caused by friction. As the surface paste of concrete wears, the fine and coarse aggregates are exposed, and abrasion and impact will cause additional degradation, related to hardness and the aggregate-to-paste bond strength. The two most damaging forms of abrasion occur on vehicular traffic surfaces in hydraulic structures. Compressive strength and hardness of aggregates are the most important factors when controlling the abrasion resistance of concrete. Abrasion damage in hydraulic structures is caused by the abrasive effects of water-borne silt, sand, gravel, rocks, ice, and other debris on the concrete surface. Although high-quality concrete can resist high water velocities for many years, the concrete may not withstand the abrasive action of debris grinding or repeatedly impacting on its surface. As is the case with traffic wear, abrasion damage in hydraulic structures can be reduced by using strong concrete with hard aggregates. The most common form of concrete degradation is corrosion of reinforcement, mainly caused by carbonation. Reinforcing steel in concrete normally doesn't corrode. This is because of the passive oxide film on the surface of the steel, due to the initial corrosion reaction. The process of cement hydration in freshly placed concrete develops a high alkalinity. In the presence of oxygen, this stabilizes the film on the surface of the embedded steel, ensuring continued protection while the alkalinity is retained. Concrete normally has a pH above 12 due to the presence of calcium hydroxide. Carbonation is a process in which carbon dioxide from the atmosphere diffuses through the porous concrete and neutralizes the alkalinity of the concrete. This reaction reduces the pH of the pore solution as low as 8.5, at which level the passive film on the steel is not stable. Carbonation is generally a slow process. In high-quality concrete, it's been estimated that carbonation will proceed at a rate of up to 1 mm per year. But the rate can be much slower in concrete designed with a low water-to-cement ratio and high cement content. Carbonation-induced corrosion is often worse when areas of building facades are exposed to rainfall, shaded from sunlight, and have low concrete cover over the reinforcing steel. Exposure of reinforced concrete to chloride ions is the primary cause of premature corrosion of steel reinforcement in marine environments and on highway and car park structures. The intrusion of chloride ions present in de-icing salts and seawater can cause steel corrosion. Chlorides dissolved in water can penetrate sound concrete or reach the steel through cracks. Admixtures containing chloride can also cause corrosion. The risk of corrosion increases as the chloride content of concrete increases. Tolerable levels of chloride content are variable according to type and surface conditions, and expert advice should be sought if chlorides are detected. Stray current corrosion, also known as stray current electrolysis, refers to corrosion caused by electrical currents flowing through paths other than the intended circuit. The process of stray current corrosion is electrolysis in nature. The extent of the damage or loss of metal is directly proportional to the magnitude of the stray current passing through the system. Underground pipelines and storage tanks without cathodic protection systems are particularly susceptible to stray current corrosion. Stray current corrosion tends to be localized, causing a concentration of pits not normally observed at localizations where the stray current leaves metal structure. Stray current corrosion is different from natural corrosion, as it's caused by an externally induced electrical current and is independent of environmental factors such as oxygen concentration or pH. Now let's take a look at the survey and diagnosis of concrete damage. A visual examination is usually the first process, and in many instances may be all that is required. You should be able to determine the presence of cracking and spalling, staining, compaction, hammer testing. If none of these are conclusive, a cover meter can be used on site. A cover meter is an instrument used to locate reinforcement and measure the exact concrete cover. If this is still inconclusive, laboratory testing may be required. Laboratory testing will provide detailed analysis of concrete. Laboratories will be able to determine and carry out microscope analysis, microcracking, cement and aggregate type, carbonation depth, alkali aggregate reaction or chemical attack, porosity of the concrete, compressive strength. Now let's look at the steps and materials involved in repairing defective concrete following diagnosis. The steps and materials include preparation, primers for steel reinforcement, concrete repair mortars, migratory corrosion inhibitors, also referred to as MCI, fairing coats, protective coatings. As with many concrete repair projects, the key to a successful outcome is in the preparation. Key techniques include removal of algae, usually with a proprietary algae remover. Grit blasting of the concrete surface and reinforcing steel. However, this may not be necessary when using polymer mortars. Needle gunning to remove defective concrete. Sawing edges at repair perimeters to avoid feather edging of repair material. Wire brushing of reinforcement if required. Polymer-modified cementitious bonding primers provide a monolithic bond between the concrete and repair mortar. They also act as additional protection to correctly prepared steel reinforcement. Concrete reinstatement is usually carried out using polymer-modified repair mortars. All manufacturers of concrete repair mortars must now conform to BSEN 1504, which stipulates that mortars are to be pre-packed, factory-produced and not site-batched mortars. For large volume repairs, flowable mortars and concretes can be used, providing adequate shuttering can be put in place. Most repairs are carried out using hand-placed mortars of varying strengths, depending on the structural requirements. In this picture, the repair has square-cut edges, and the steel and concrete have been prepared and primed properly. Large repairs generally use a flowable mortar, poured into shuttering and allowed to cure. The shuttering is then removed to reveal the reinstated repair. An MCI can penetrate to a depth of 75 to 80 millimeters, and when it comes into contact with the reinforcing steel, it has an ionic attraction that forms a protective layer. An MCI's affinity to steel is stronger than water, chlorides and other corrosive contaminants, resulting in long-term protection. Fairing coats are generally a thin-section skim coat of approximately 2 millimeters. As well as filling blowholes in concrete, they're applied over concrete surfaces to cover patch repairs prior to the application of a coating system. Once concrete repairs have been carried out, including a fairing coat, a protective coating may be applied. There are many types of coating available. The selection will be dependent on the performance and aesthetic requirements. The most commonly used coatings are anti-carbonation coatings, in one form or another. As well as having resistance to carbon dioxide, other criteria may be important, such as, does it need to be elastomeric? Does it need to have crack bridging properties? If crack bridging properties are required, to what degree? Will you need 0.2 mm live crack accommodation, 1 mm, or 2 mm? If the coating is for decorative purposes only, anti-carbonation properties might not be needed, as masonry paint may be all that's required. This shows a typical concrete repair project. Reinforcement, corrosion and spalling concrete are clearly visible. Following preparation, the concrete has been repaired with an appropriate mortar, followed by a fairing coat and a protective coating. As you can see, the building has been restored to its former majesty by following a few simple steps. The success of a concrete repair project can hinge on the ability and experience of the contractor employed to do it. Many manufacturers have built relationships with good contractors over years. It makes sense to capitalize on this experience when selecting your contractor. You should now have a knowledge and understanding of client objectives, including lifetime costs and budgets, visual assessments to determine the extent of the damage, in-depth assessment, causes of structural degradation, specific repair methods and materials required, the importance of using suitably qualified contractors. For any technical inquiries, or to find out more about the methods involved in concrete repair and protection, contact our technical department on 01279 638 700 or email tech at ronacrete.co.uk. We hope this CPD presentation was useful to you. If you'd like to receive a certificate showing you've completed this CPD presentation, please fill in the form below and a certificate will be sent out to you.